This is Lab Report 9 by Alex Caballero. The problem. The problem of this lab was to determine the period of oscillation in the y direction from the measured and predicted data and putting the spring into the system and calculating the corresponding change in the spring potential energy. Problem continued. This lab examines the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We use the fundamental principles to predict motion: the momentum principle, Newton's second law, and the energy principle of thermodynamics. Here's the tracker showing the position of the spring. Here's the code that I used for the lab. I edited many things, including the observation measurements and many gravitational forces, and also the delta T. I also commented the optional visualize motion measurements for video analysis to include the CNT equals CNT plus 1, which created the graph plot T, T. I also included the ball.pos.y and ball2.pos.y. This is the VPython. And here it shows the module. Pull the graph up a little bit. The connection of the model to experimental data. The model shows the idealized version of the spring unaffected by air resistance, so the spring would continue at constant motion. With this in mind, the total mechanical energy is still conserved, that is, delta E equals 0. The model correctly displays the data represented by the video. This is proved by the model following the motion of the spring and weight in the video. What does it mean? The period of oscillation was found by examining the x component, and the period of oscillation found by examining the y component are going to be different because there are different forces acting in each direction. In the x component, the force acting on the ball is the spring force. In the y component, the force acting on the ball is gravity and the spring force. I used the graphs to find the period of oscillating masses in the x and y directions. One period is from trough to trough in the graph. To find the numbers, I rolled the mouse over the graph to find the time differences of the simulation periods. To find the difference, we did the final time minus initial time, as you can see below. The y position was a change of 0.01 seconds, and the x position was a change of 0.049 seconds. Since the new system incorporates the ball, the earth, and the spring, there are no outside significant surroundings, so no work is done by the surroundings. This is because for the work to be done, energy has to leave the system and go into the surrounding object. Yes, the energy principle is satisfied because the change in the energy is 0, as all the energy remains in the system and just changes form. The sum of all the energies will be less than the sum of the energies at the origins from the original location. This is because potential energies have to do with interacting objects, so you get different values based on origin choice. The physics of the system doesn't change. The change in energy quality stays the same. This includes the object behaving the same and the graphs staying the same. The following tracker shows the change from the origin and the fixed point to 7e to the negative first below the fixed point. And here's the tracker with the changed origin. The final results. Our lab agrees with the energy principle of Newton's second law and conservation of energy. The change in energy is equal to work done by the surroundings, so when we include the earth, the ball, and the spring in our system, because of this, delta E equals 0 for all cases. Therefore, changing the origin did not change the physics, but just the values, which in turn changed the potential energy. Thank you.